So let me first say that this may not be your typical sabbatical talk. I've attended talks in this department that started with pictures from sunny places, and the best I could do is to show you this fake picture. So I didn't do any of these things. I did start some marathon training, so that's going well. So let's see what I actually did. And I tried to climb two ladders. One is the ladder of human action, and one is the ladder of causation. The first one is really me trying to move from knowledge-free or tasks requiring little knowledge to knowledge-based human action, from the ACT-R cognitive architecture to the SOAR cognitive architecture, and from milliseconds kind of tasks and effects to days, weeks, or months. With regard to the ladder of causation, I wanted to move a bit away or higher from randomized controlled trials or from typical experimental method that we used in psychology to counterfactual simulations, and from toy lab tasks to geopolitical forecasting. So this is a table that you might have seen, is the time scale of human action from Newell in his book, Unified Theories of Cognition in 1990. This is me adding this ladder, trying to span starting from cognitive band, where my background, my instruction is, and trying to go to rational and the social bands. So the cognitive band is obviously what you all know, perception, cognition, as we study it, and it concerns itself with tasks that are in the time range from 100 milliseconds to 10 seconds. The rational band contained decision-making kind of tasks and more realistic tasks that can go up to hours, and the social band can go up to months. Newell says that intelligence is really located in this rational band. That's where goal-directed, knowledge-based, and adaptive action takes place. And with regard to the social band, he kind of shies away of that, and most cognitive modelers shy away of the social band, at least the cognitive modeling approach that is rooted in cognitive architectures. And Newell's reason is because this level has weak systemicity. But I tend to agree with more recent work by Thomas Malone at MIT, who thinks that there is actually opportunities, that's the place for collective intelligence, even higher intelligence than individual intelligence, and the superminds, particularly when you combine humans with technology as well. What's critical of this attempt of mine is really moving toward understanding knowledge-based tasks. And here I give a quote from Alan Newell: "It is of the essence of adult human minds that they bring a vast amount of knowledge into every situation they are in." We try, when we run experiments in cognitive psychology, we try to limit the amount of knowledge that people bring to the lab or to the task, or sometimes randomize them to reduce the impact of that knowledge, or give them artificial tasks so they don't have prior knowledge. But that makes our work less ecologically valid and relevant to the real world. So here is the ladder of causation as drawn by Julia Pearl and Dana McKenzie in their book, The Book of Why, which I highly recommend. It's an AI book, but it's accessible to psychologists as well. So according to Pearl, we have a ladder with three rungs. One is the association rung, where the common machines and the animals are placed. And this is based on perception, seeing, observing, and finding associations between objects or events. Then there is the intervention rung, where people are intervening in the world and observing what happens. And then the last level, where modern humans are, is the imagining level, where people engage in counterfactual reasoning. And they ask questions like, what if I had done this, and why? So here's an example of counterfactual reasoning as defined by Lewis. If A were the case, C would be the case. So this statement would be true in the actual world. Yeah, we can imagine that statement, but it would be true in the actual world. If some A world where C holds is closer to the actual world than is any A world where C does not hold. So to bring this home to the realm of running experiments in psychology, let's rephrase it like this. If subject S1 were administered HPO, human performance optimization, intervention I1, her performance P1 would be high. So as a psychologist, I want to make this kind of reasoning, and I want to be close to being factually true. So this is true in the real world if and only if a subject S2 who is similar to S1 was administered intervention I1 and her performance was high. And this conjunction is critical here, another subject S3 who is dissimilar to S1 was also administered the intervention and his performance was low, or at least it wasn't as high. So I'm going to present two studies. One is just to show and to familiarize you with geopolitical forecasting task. And another one is really about counterfactual predictions. So the first study is a human performance optimization empirical study. So it's a study that we actually ran. And it can be placed on the cognitive, rational, and social rungs of the ladder of human action. And also it can be placed on the association and intervention rungs on the ladder of causation. So we're not yet on the imagination or counterfactual rung, but we are setting the stage for that. So I'm going to go quite fast here, but please stop me if you have clarification questions. So here is the task. The geopolitical forecasting task is part of intelligence analysis. It is done frequently in the intelligence community or in business, wherever it matters. If competitors can get ahead of you, it is important to be able to tell what will happen in the future with some accuracy. It's an information-intensive and knowledge-intensive task. It's heavily informed by knowledge. It's uncertain, obviously, because it's about the future. It takes place over an extended time course during which the world might change and relevant but also irrelevant evidence accumulates. It's high workload. One individual may engage in multiple forecasting tasks. And it has a social collaborative dimension. One task may be attempted by a group of cooperating and/or competing forecasters. And there are interpersonal and human-machine interactions. It is hard to imagine nowadays forecasting without the use of technology. So forecasts are usually the product of socio-technical system that combines human and machine capabilities and goes beyond the traditional function allocation methods like MABA, men are better at, machines are better at, and goes into the realm of human-machine teaming and human-machine co-evolution. So the human may be doing sense-making, anticipatory thinking, but the machine assists with information search time series analysis, causal models, or aggregation of multiple human forecasts. The humans also may be vulnerable to cognitive load and cognitive biases. So in high workload conditions, forecasters have been shown to exhibit more herding and less granularity. Herding is non-independence between different forecasters, so influencing each other in a not necessarily positive way. So task offload tools can be used to delegate some task demands to automation. That has been used successfully in many human factors applications. However, delegating too much can reduce the opportunity of the human to engage in high-level processes and can harm motivation and performance. Thus, a hybrid tool must strike a balance between offloading task demands and maintaining user engagement. So this is a study performed during an IARPA tournament, hybrid forecasting competition. The forecasting problems, I will describe them, I will give you an example later. They are questions that have 2 to 5 discrete mutually exclusive outcome options, and each outcome option has to be assigned a probabilistic forecast. There are 6 domains there. Participants can choose, and this is critical, they can choose what tasks to solve, how many times to update their forecasts, and what tools to use. And the participants here are volunteer forecasters or Amazon Mechanical Turk workers. As performance score, we use the Breyer score, which is an error measure, basically is the difference between the forecast and the actual outcome. We also use an accuracy score, which places the Breyer score in the context of a crowd score. So it's the difference between the crowd and the individual score. And here are examples of the tools that forecasters can use. I'm going to go into the customized alarm and customized rule of thumb rules here. These are tools that notify participants when relevant information, for example, the value of a particular indicator, changes. So if some information changes in the environment, the participant is notified and also recommended a forecast update. The rule of thumb detects changes in relevant information in the environment and update the forecast automatically and also notify the participants. So here are examples. This is a forecasting question. What will be the daily closing spot of price of Brent crude oil on March 1st, 2018? So this is the question. It has some details here, and these are the possible outcomes, and the subjects have to assign probabilities to these outcomes. Here is the forecast, the crowd forecast history. Here is how the crowd, how many participants forecasted that particular question. So each user can see how others have forecasted the question. But to minimize herding, this information was provided only after they made their own forecast. These are indicators, statistics that are relevant to the forecasting problem. You see here the trend over time of that particular price. And these are queries that extracts data from relevant sources and present it to the user. The users can edit those queries, can save them, can run them, let them run automatically, and can also share the results with others. These are the alarms or alerts. The user have to specify a rule, and the system detects the changes in the environment that the rule wants to detect and notifies the user. So here is an English version of the rule. If my forecast for yes is below the crowd's by more than 10% points, and the crowd's forecast for yes is about 50%, then alert me immediately. With regard to personality variables, some were found to correlate with forecasting performance by previous authors, like cognitive reflection test, actively open-minded thinking scale, and need for cognition. And we also use a lot of measures of forecasting behavior, like the number of problems forecasted, the number of forecast updates per each problem, and the frequency of usage for each hybrid feature. So here, we were thinking that using hybrid tools should reduce the cognitive load, which in turn should allow participants to make more and better forecasts. And creating these tools, in particular alarms and rule of thumbs, should encourage the users to develop intuitive causal models, which should improve forecasting performance. So H1, the first hypothesis, says that use of hybrid tools improves forecasting productivity, that is the number of forecasts generated and the frequency of updating. And the second hypothesis says that the use of hybrid tools explains additional variance in forecasting performance above and beyond psychological variables. I'm going to present the results briefly. The first disappointing kind of result, only 319 users out of 839 used one of or more of those hybrid tools. So that was unexpected, but that turns out to leave a lot of room for our counterfactual reasoning study. So with regard to effect on productivity and performance, participants who used the hybrid tools submitted more forecasts, forecasted a wider range of topics, updated forecasts more frequently, and obtained lower Breyer score. So Breyer score is an error measure, lower is better. So they were performing better. Now, it was unclear whether these findings are driven by the availability of those hybrid tools or by motivation. And it was known that motivation, particularly the frequency of forecast updating, predicted forecasting performance. It has been found before. So we developed two alternative causal models. One says that the highly motivated participants made a larger number of forecast updates and used the provided hybrid tools, which in turn increased performance. Or the second model says that the hybrid tools increased the participants' motivation to make updates, which in turn increased performance. So here's model one. Motivation indeed increased the use of hybrid tools, but that did not increase performance when psychological traits and motivation were considered in the model. So even though we saw this effect when we looked in isolation at hybrid tools and performance, the effect disappeared, became non-significant when all these other variables were included in the model. And model two was a better model, the model that says that actually the availability of the hybrid tools made people work harder, and that in turn increased performance. So we replicated previous findings, and we demonstrated, in addition to that, the hybrid tools made users more productive and more accurate. However, this effect, we expected this effect to be additive to the effect that were already known, and instead we found that the relationship between hybrid tools and performance was mediated by motivation. These findings must be interpreted with caution because the use of hybrid tools was optional and only a minority of participants used the provided hybrid tools. The decision to use hybrid tools might be confounded by other factors such as trust. And the model suggested that hybrid tools encouraged participants to do more work, which in turn improved performance. In particular, the alarm and the rule of thumb editor challenge participants to create their own intuitive models of forecasting and turn these models into support tools. So these results highlight the importance of providing tools that engage users and enhance their cognitive activity. So instead of tools that totally take away the effort from users, these are tools that actually enhance their cognitive activity. And these tools aim to strike a balance between user effort and automation, and ultimately they achieve the goals of human-machine symbiosis and co-evolution. Okay, so that was the first study. And now we're trying to go into this third rung of the ladder of causation. And this is a human performance optimization simulation study. So we don't run any more subjects. Again, it's placed on the cognitive, rational, and social rungs on the ladder of human action, but it's also placed on the third rung on the ladder of causation, because now we're making counterfactual predictions. So here is an overview of the counterfactual reasoning approach. We may have a couple of interventions, I1 and I2. We have a number of subjects that we run in those interventions, but we also have a subject or more, the ones that are colored here in orange, that have not participated in those experiments. But we have a way to tell how similar they are to the participants who did participate in those interventions. And we also have a number of tasks. Some of them were executed by the subjects in the experiments, and some are new tasks that we don't know, we have no data on, but we have a way to tell how similar these tasks are to the other tasks that were actually used. And what we want to, and we have performance scores. We have performance scores. The blue ones are performance scores for the subjects who did participate in the tasks that they did attempt in those experiments. And we want to tell something about the performance of the subjects who did not participate, either on tasks that were used in the study or on novel tasks. We want to say something about these orange scores. So we can answer counterfactual questions like, if S3 were assigned to intervention 1 and performed task T4, what would be her performance score, and so on. So here is an example of a task and what kind of information we have about the task and about the users that we can use to assess those similarities. So this is the task description, but we also have some details about that task. And users, when they forecasted those problems, they generated rationales. They told us why they forecasted them in a certain way. So what we do, we create bags of words for the task descriptions and for the rationales, and we use those to assess similarities between tasks and between users. And we use machine learning techniques from the natural language processing domain, like latent Dirichlet allocation, semantic embedding with fast text, tool that is used at Facebook AI Research Lab, and semantic embedding with Goose, tool that is used by Google. It's called Google Universal Sentence Encoder. I'm not going into details. This is interesting stuff, but you can find, and we run a little study with these tools. But I want to go into the more interesting things here. So how do we, first, we want to see if this additional information that was not considered, task descriptions and user-generated rationales, if this additional information can explain the residuals of the original experiment. So in any experiment, there are residuals, that is unexplained variance in the dependent variable. And if we can benefit from more information, maybe we can explain some of that residual information. So here we call this information about the knowledge that the users might have and the compatibility between user tasks. We call this contextual information. And as contextual information, we use task descriptions, user-generated rationales, personality traits, and we also use the choices those users make in the experiment. So as preparatory steps for this counterfactual reasoning work, we want to be able to say that we can predict performance of in-sample users. In-sample are subjects who have participated in the experiment on out-of-sample tasks. These are tasks that were not used in the experiment. And also we want to say that we can predict performance of out-of-sample subjects, so subjects who have not participated in the experiment. Now, for the reasons of this study, in-sample and out-of-sample really boils down to the leave one out cross-validation method. So we leave one out, one subject or one task out, and we iterate through all of the tasks that way. So we want to be able to explain some of that residual variance. So the first hypothesis says that applying this contextual knowledge to the training samples allows us to predict performance of in-sample users on out-of-sample tasks contexts. And for that, we design this new variable that we called inferred task knowledge, based on user-related and task-related contextual information. So inferred task knowledge is a weighted average performance score on the attempted in-sample tasks. And the weights are the semantic similarities between the out-of-sample task and the in-sample tasks. I will show you an example of this to make it easier to understand. So this is the out-of-sample task, task I, and we have a number of in-sample tasks. So for this particular subject, we have the tasks that that subject has attempted. And we have the performance of that subject, the scores for those tasks. So we want to and we also have the similarities between these tasks and all the other tasks that the user attempted. And we want to be able to tell what knowledge the user has for task I. And inferred task knowledge would be a weighted sum of the performance scores, where the weights are these similarities between the task at hand and the in-sample tasks. And here we validate that. And so for each out-of-sample task, this is the out-of-sample task performance on the y-axis. We see if the inferred task knowledge, which was computed as I explained, predicts that task performance. So this is the ground truth, and this is the inferred task knowledge. And we get a prediction there with an adjusted R-square of 0.18. So we are able to predict how the subjects will do on a task that they have not attempted yet, based on the task that they have attempted. Now, the following hypothesis says that if we apply contextual knowledge to the training samples, we will be able to predict performance of out-of-sample subjects. So now we're interested in predicting the whole subjects, the whole new subject performance. And here we compute an inferred knowledge similarity variable for the withheld, for the out-of-sample subjects. So we try to find a match for that out-of-sample subject based on how similar that subject is to in-sample subjects that we actually have information about. So I will explain this in more detail here. So basically, inferred knowledge similarity leverages information about task choice and task accuracy. Since forecasters could select what tasks to perform, we get this overlapping between individuals, partial overlapping between individuals with regard to what tasks they attempted. And we also know their performance on those tasks. So for example, forecasters 2 and 3 overlap more than forecasters 1 and 2. So that's one information we consider. And here we look at how much overlap between forecasters in terms of tasks that they chose to execute is. So we call this the intersection, the shared tasks, the intersection set, and the unique tasks that they perform, the disjunctive union set. And inferred knowledge similarity is the sum of the accuracies in the intersection set minus the sum of the accuracies in the disjunctive union set. So this similarity increases with the size of the intersection set. So the more tasks they performed jointly, or they both performed, the higher the similarity. And also, if they perform those tasks with higher accuracy, the more confident we are that they actually have knowledge, the same kind of knowledge for those tasks. And that similarity decreases with the size of the disjunctive union set and the lower accuracy. So to validate the prediction, we again hold out one subject and predict that the performance of that subject based on the performance of subjects in the sample that we matched with the withheld subject. And we get an adjusted R-square of 0.12 prediction. For hypothesis 2, we want to predict the out-of-sample performance. So we explain some of the residual variance based on this contextual information, and we want to predict the out-of-sample performance. So basically here we combine the similarities between tasks and the similarities between individuals and see how well we're doing overall. So here the data points are subject task units, and the residual score is here on the y-axis. And we see that we can explain 17% of the variance in the residual performance for an out-of-sample subject on an out-of-sample task based on how the subject performed on similar in-sample tasks and how similar in-sample subject perform on the out-of-sample task. So basically here we're combining the two metrics. Now, having established that, we can say, what if now we intervene? We imagine that we run an experiment in which we change the way we allocate tasks to individuals. And later, I will also show how we can allocate individuals to conditions or individual to interventions. So here we compute the upward or downward counterfactual scores for each out-of-sample subject. The upward counterfactual score is the score that includes for each subject only the tasks that the subject is predicted to perform well at. And the downward are the tasks where the subject is predicted to perform poorly at. So here we hypothesize that both upward and downward counterfactual scores will have lower variance than the original performance scores. And the upward counterfactual score is significantly higher than the downward counterfactual score. And that is indeed what we obtain. So here is the control condition. Here is the prescience condition where we use those hybrid tools. And this is the condition, this is a hypothetical condition, right, that we run based on our predictions of how people would have done on tasks. And so we select here only the tasks that they are predicted to do well at, and here only the tasks that they are predicted to do not so well at. And we see the difference made in accuracy. So inferred task knowledge and inferred knowledge similarities are useful. This is evidence that some proof of task knowledge from past accuracy on similar tasks is necessary to predict future task performance. In knowledge-intensive tasks like forecasting, it may not work as well in tasks that are less knowledge demanding. These are those tools, LDA and fast text, do better at differentiating individuals than differentiating tasks. And psychometrics provided useful complementary information. This is important because psychometrics are easy to collect and they are task-independent information. Now, let's put some additional constraints on counterfactual reasoning. If we consider, so we've run this post hoc after the experiment has been run. But what if we do this as the experiment is run? So these are experiments run over months. So the participants get this problem. They are asked to forecast what would happen 3 months from now. And during these 3 months, they can collect information, they can update their forecasts and so on. They could collaborate with others. So what if we use this methodology to run counterfactual reasoning as the experiment is run? So in that case, we cannot use information from the future. We have to use only the data that was collected up to the point where we want to make a decision. And in addition to that, we may want to use not just matching, the matching approach that I presented so far, but also a model-based approach that is recommended by Judea Pearl, an approach based on structure equation modeling, which basically fits a causal model to the data and then uses the model parameters and the factor scores to generate counterfactual predictions. And I will show an example of that. So now let's take some specific counterfactual questions that we may want to answer for theoretical and practical reasons. For example, the first question, for subject X who participated in the HPO, Human Performance Optimization study, but only performed tasks M, N, and O, what would be the predicted performance score on tasks P and Q? How accurate would this prediction be? So here is a cherry-picked subject, just to illustrate this. This subject has done tasks T1, T2, and T3 in this order. Now, to predict T1's performance from T1's performance weighted by the similarity between T2 and T1. So this is the inferred task knowledge measure. So at T2, we can only use information about T1 because T3 has not been conducted yet. And at T3, we can use both T1 and T2 because we have that information. Now, that was a cherry-picked subject. What if we use all the subjects? And this is the data for all the subjects. And we're not doing as well as before, again, because we're restricted in what information we can use. This is only information about the inferred task knowledge. Now let's take another question. For a particular subject who did not participate in the study, but could be matched based on contextual information with subject who participated, what would be the predicted overall performance score across all the tasks they performed? how accurate would this prediction be? And again, this is a cherry-picked subject. And this subject, the accuracy, the score of that subject is on the y-axis. And on the x-axis, we have the scores of subjects who were matched to this subject. And they were matched based on what tasks they did at what time, what tasks the other subjects have selected, and how well they did on those tasks. So we have different subjects matching this cherry-picked subject depending on particular time points and the particular tasks they did. And of course, this is cherry-picked, we get a very good prediction. But how are we doing with all the data? And here are all the subjects and tasks with the data points being subject task units. And we're doing reasonably well, 0.14 or 14% of variance explained. If we restrict this to only subjects or aggregate across tasks, we get even a better score of 27% of variance explained. So we're skipping question 3 for now. Let's take another question. If subjects X, Y, and Z who did not participate in the study were given only tasks they were predicted to do well at, and remember, this is running in parallel with the actual study, would they perform on average better than the subjects who participated in the study? Would the variance of their performance score be lower than the variance of the subjects who participated in the study? So we're interested in lowering the variance because that's error variance, right? So lower variance is better. And question 5 is similar, but in this case, we only give tasks that they were predicted to do poorly at. And of course, we expect performance to be worse and the variance also to be lower. And we get results that are similar to the ones that we got with full data, maybe not as strong, but still significant. Now, this matching approach that I presented is good. It takes us this far, but is limited because it is agnostic with regard to the causal relationship between variables. We're just matching tasks and subjects. So it would be good to use also information about how variables are related. So here we develop 2 structure equation models for a particular data set. This is a different data set than the one I presented before. And now first we develop 2 models to check which model is better and pick the better one. And then we use the better one to estimate, to make counterfactual predictions, to use the parameters from the better model to make counterfactual predictions. These are the 2 models. They are not fundamentally different. So basically, motivation can be a confounder for the relationship between hybrid and accuracy, or it could be a mediator. And the second model, again, is better. Motivation appears to be a mediator between hybrid, the intervention, providing hybrid features, and accuracy of forecasting. So basically, people were working harder because they were provided with those hybrid accuracy, and that was reflected in better performance. So we picked this model that was proven to be a better model. And I will show this example of how we make counterfactual predictions for one particular subject, again, a cherry-picked subject. And we see that this subject did not use, apologies for the way these numbers are shown here. This subject did not use hybrid feature much. So these are some of those hybrid tools, and these are some of the hybrid tasks that they were using. For example, they were ranking rationales. So we're going to assume that this subject used a lot of these features and also did this rational ranking a lot more frequently than they did in fact. So we are going to give them higher numbers for the frequency of use of hybrid features. Now, if we do that, this is a hypothetical intervention. So we have to cut this link between the use of hybrid feature and psychology traits, because now we're altering this variable, right? It's like an intervention. So we can't really assume a correlation with psychological traits. We are making this subject use those features more frequently. And so that will affect their factor scores for the use of hybrid feature, will change it, will increase. Due to this relationship, that will also increase their motivation, and eventually that will also increase their performance. Now, the change in outcome, the change in performance is relatively small, from 0.34 to 0.41, relatively to how large the change in treatment was. So here we made really large changes, and they propagated through these path coefficients, and they resulted in rather small performance. Even though this is a significant change, it is rather small. So this tells us that had subjects used those hybrid features more often, they would have benefited more. So the difference made by this treatment, this intervention, would have been more visible. Now, that was for a cherry-picked subject. How do we do with all the subjects? Here, again, we create this upward counterfactual condition and downward counterfactual conditions. These are hypothetical conditions, hypothetical interventions. So we're assuming we're intervening by asking people to do either to use those hybrid features either very frequently in the upward counterfactual condition or very infrequently in the downward counterfactual condition. And we obtained higher performance in the upward and lower performance in the downward, but the effect size is rather small. So this tells us that even in the best case scenario, well, this is close to best, is not the best, to preserve some variability there. But even in a very optimistic scenario, this intervention would have helped only by a little bit, significantly, but only by a little bit. So this may be useful information for a theory or for practitioners. Now let's go back to counterfactual question 3. For subject Y who did not participate in the study, but could be matched based on contextual information with subject who participated, and could be predicted to do well or not so well on each task, what would be the predicted effect of the experimental intervention? And would this prediction be less accurate if information about subject-task compatibility were missing? So here we're using the ACE data set. It's a different data set collected by Mellers and others at the University of Pennsylvania. This is a data set where we have 3 conditions, and we have sufficient data for all 3 conditions. And again, we build a structure equation model. This is the dependent variable, again, forecasting accuracy. We have 2 mediators here, number of updates or number of problems attempted. We have the treatment here, which is training with 3 conditions. And we have psychological traits, which were measured pre-treatment. Again, we're using leave one out cross-validation. And here we can see that we can make predictions for new participants based on this model. And they are significant, but not extremely strong. So, but keep in mind that this time we did not perform any matching. This is based only on the structure equation model. And this is under the assumption that previous records may not be available. So you may not have an experiment. If you have only the model, you can make this kind of predictions. So we're looking now at a model in which we use matching, but matching is only based on psych traits, on psychological traits, and self-rated expertise. So this is information that you can collect independently of asking them to do any kind of forecasting. Just ask them what they think their expertise might be for those tasks and what are their psychological traits. So in this case, we're getting better results, obviously because we use more information. But if we only match based on psychological traits, if we leave out that self-rated expertise, we still get a good prediction, but lower. So now we're going to the last part, and this is the last point I want to make. We can actually assess the treatment responsiveness of a particular subject. So how would subjects respond to a particular treatment, how likely they are to respond well to a particular treatment. So this is, we're going into even more hypothetical realms by not only saying how participants would do in a particular condition, now how would they do in different conditions? So here we have treatment responsiveness of subjects X, Y, and Z who did not participate in the study, and I will show how we compute that responsiveness based on contextual information. If we have that responsiveness, what would be their actual response to the intervention? And how accurately would the actual response be predicted from their responsiveness? So for treatment responsiveness, we again we computed for an out-of-sample participant, and for each training condition, so we have 3 conditions, using the model and matching was done only on psychological trait and self-rated expertise. Now, treatment responsiveness was computed as a difference between predicted accuracy for a training condition and the control condition. So now we're predicting really effects that are differences between conditions. For example, the treatment responsiveness of participant X is their predicted accuracy if they were assigned to the probability training condition, minus their predicted accuracy if they were assigned to the control condition. And here is the predicted response to probability training, one of the conditions. That responsiveness predicts weakly the actual effect of probability training. So the actual effect here is not entirely a ground truth measure because we didn't know how each participant in a training group would have actually performed if they had been assigned to the control group. So we actually here have to estimate how they would have performed if they were in the control group. So not only we leave out the subject, we also try to estimate how they would have behaved in a different condition. And this is for the scenario training. And here is a case where we can imagine that we were able to select participants based on their predicted treatment responsiveness before the study was conducted. And if we were able to do that, we would have observed a stronger effect of training on the accuracy in that study. So if we were able to say this subject is better assigned to this particular condition, then we would have obtained a stronger effect of that study. So in black, we have the actual effect. In red, we have the effect that would have been obtained if this kind of filtering would have been used a priori. And this may be important for practical purposes. For example, when your intervention is a treatment, you want participants to benefit maximally from the condition they are in. So, in conclusion, counterfactual reasoning based on subject, task matching, and structure equation modeling can be used to extend the range of conclusions that can be drawn from human performance optimization experiments. For example, we can conclude that if participants made greater use of the hybrid forecasting tools, as in the upward counterfactual condition, their accuracy would have improved significantly. However, since the effect size is small, the treatment would have had a small effect on the outcome, even under the assumption that all participants would have used the provided tools frequently. If participants were assigned tasks that they were predicted to do well at, they would have performed better. And if they were assigned to interventions that they were predicted to be responsive to, they would have responded better. However, this kind of approach and the modeling that is required requires substantial background knowledge for model development and counterfactual reasoning. And I'm going to stop here. I'll take any questions.
Jan, to Scott. So in your first study, you had two hypotheses, and neither hypothesis said anything about performance, and yet your conclusions ended up talking a lot about performance. So was it just a difficulty and it was about using hybrid tools, and so did your hypotheses not include performance because, well, I mean, was that on purpose, or was it because partly that those kind of predictions, those kind of hypotheses that would include performance, they have to make assumptions about how good those hybrid tools are?
So the hypothesis included performance.
I didn't think they did.
You're referring to the first or the second study?
First study. It was early on.
Yeah, so we hypothesized that having hybrid tools available will increase performance.
Well, I mean, you had performance just in terms of they would make more predictions and update them more frequently, but you didn't have anything about accuracy.
We actually did, yeah. Sorry, I didn't make that clear. But we looked at their productivity and accuracy. So we call this performance in general terms. But yeah, we looked at how many predictions they made, how frequently they updated. That's called productivity. Right. But we also looked at how accurate they were. So one of these predictions was actually confirmed. The people who had access to those tools, they did get lower Breyer scores, that is higher accuracy.
Right. No, I noticed that in your results that's what you talked about, but I didn't think I'd seen anything about accuracy in your hypotheses.
Sorry, I may have gone too fast, but
I was just wondering, because partly how do you are those hybrid tools validated in some way as having a certain level of value to them? I mean, can that be done independently?
They were not validated. This was the study was aimed at that, and they were also not tested individually. They were tested as a whole. So, as I said, the forecasters could have picked any tools, and they could have chosen any tasks to do out of a menu of tasks and tools.
Mm-hmm.
So it leaves little room for very strong conclusions.
Right.
But the general conclusion that can be taken from that study is that providing some tools help people to think, maybe do more processing about the task, and eventually perform better. Not a lot better, but better.
Okay. Thank you.
Other questions? If we don't have other questions, I will have to cut it here because we are a little bit late. Sorry about that. Thank you for your participation, and I will see you next week.